Namaste and welcome back to the lecture on linear algebra through geometry. We were looking at two dimension vectors in in two dimensional space, and we looked at various transformations of these vectors and a lot of other stuff. And towards the end of the last lecture we had a couple of questions that we had asked, like how do we look at the what do we call it, when you try to solve a system of two equations in two unknowns, how does it look, how do we interpret that in terms of the vectors that we have studied? Is there a connection between that and stuff? So what we are going to do is we are going to look at a new perspective of looking at the system of equations, which is basically looking at the system of equations through the columns or from the column perspective. Normally what we do is when we look at the system of equations, we end up reading row wise. We say that okay, the first row is basically one equation, the second row is another equation, so we basically do that. But now what we are going to do is we are going to look at the system of equations through a column perspective. So what does that mean? So that is what we are going to look at in this lecture. And geometrically, how does it look like? What is it to say that a system has a system of two equations and two unknowns? What is it to say that it has unique solution, it has infinitely many solutions, and or it has no solution at all, like the idea of inconsistent system. So how are we going to capture all that? And that is what we are going to look at in this lecture. So yeah, let us just take a simple example, like we start with our usual example where I have let us say 2x1 plus x2 is equal to 3, x1 plus 2x2 is equal to 3. So let us take it this way. Now when we interpret this as a system of equation where we have Ax equal to b, it is always this, where we have the coefficient to be populated, coefficients to be populated in the matrix A 2 1 1 2, and we have the unknowns which are basically put in a column format. It is a column vector, and on the right hand side you have the b vector, which is basically 3 3, right. This is what we have. Now it is interesting to see that if you look at the system of equations and you look at the columns, the first column of this matrix A, which is 2 1, it always seems to get multiplied by this factor x1, and the second column of the matrix 1 2 seems to get always multiplied by the factor x2. So and that is exactly where we are going to move towards the column perspective of viewing a system of equations. So what are we going to do? I am going to write this as x1 into 2 1 plus x2 into 1 2 is equal to 3 3, and this format of writing like x1 into 2 1 plus x2 into 1 2 is equal to 3 3 is not something new to us, in the sense that if we call, if u is a vector which is equal to 2 1 and v is another vector which is equal to 1 2, then we say that w, a vector w, we say w is equal to, let us say alpha u plus beta v, where alpha and beta are scalars, we say w is equal to alpha u plus beta v as is a linear combination of the two vectors, is a linear combination of the vectors u and v. And essentially what we see here is the same thing, whatever that we see here is essentially the same thing. What does this mean? We are looking at writing this vector 3 3 as a linear combination of 3 3 as a linear combination of the vector 2 1 and the vector 1 2, sorry. So what is it that we need to do in this case? by solving the system of equations, what we mean is here we need to find out the values of the unknowns, whereas in this case when you look at it in the vector format, it looks like we need to find out those scaling factors x1 and x2 such that the linear combination of x1 and this vector 2 1 and 1 2 gives me this vector 3 3. That means equivalently from the system of equations we are going to write, we need to find the scalars, find the scalars x1 and x2 such that x1 into let us say 2 1 plus x2 into 1 2 gives me this right hand side vector 3 3. Now in general we can do it this way. So in general if A is a matrix with let us say 2 columns, let us say A, the first column is A1 and second column is A2, I will write this as A11, A12, A21, A22 and let us call this vector A1 as A11, A21 and the vector A2 as A12, A22. Now what are we looking for? We want to look at if by Ax equal to B we mean, by Ax equal to B we mean B is equal to x1 into the first column vector or the first column of A plus x2 into the second column of A. That means we want to find out these scalars x1 and x2 such that B can be written as x1 A1 plus x2 A2, where A1 and A2 are respectively the first and second columns of the matrix A, right. Okay. Now in our example, in our example where we had this 3 3 which was equal to x1 into 2 1 plus x2 into 1 2, we can actually draw the graphical representation of this and then try to figure out if you are able to get a value of value for x1 and x2. So if we take this let me call this as the E1 axis, let me call this as the E2 axis, or let me call that as x1 x2 axis. Now I am going to have this 1 2 3 4 5 6 7 1 2 3 4. Let me mark these points 1 2 3 4 5 6 7 1 2 3 4. Now what we have is the vector 2 1, 2 1 is going to be this vector and 1 2 is going to be this vector. Now what is required is what is that value of x1 and x2 such that if I take the linear combination of these two I end up getting the value 3 3. It is easy to see that if you draw this, this is the vector let us say this is the vector A1, okay, this is the vector A1 and this is the vector A2. We know that if you want to add two vectors you move one of these vectors to the head of the other vector, that means the tail of the one vector you move it to the head of the other vector. So what we do is I am going to move this guy A2 vector parallelly to such that I move to the head of A1 vector, and now what we see is we get to see that the resultant is exactly 3 3, that is the vector that we are looking for. So what it says is we see this 1 time A1 plus 1 time A2 basically gives me 3 3, and that is the solution that we are looking for. So basically if you are able to so what it says is if you are able to find out a value for at least one value for the scalars x1 and x2, then we say that the system is consistent and that there exists solution for this. That means the right hand side vector that you have, which is b, can be expressed in terms of the linear combination of the column vectors or the columns of the matrix A, right. Let us take this second example. Let us take example 2. I am going to have this example 2 where I am going to look at 2x1 plus x2 is equal to 3 and 4x1 plus 2x2 is equal to 6. This is the example that I am going to have. So, this is also something which you would have seen in your previous lectures. So, we are going to look at this. I am going to write it in the same way as I wrote the column picture. I am going to get this as x1 into 2 4 plus x2 into 1 2 gives me 3 6. Now, let us try to draw these vectors. Let us look at these vectors, how do they, and then check like what are the values for x1 and x2. So, what are we essentially looking for? We are looking for scalars x1 and x2 such that the vector 3 6 can be expressed as a linear combination of 2 4 and 1 2, which is again the same way. So, let us look at that. So, let us take it here. This is the E1 axis and that is the E2 axis. Sorry, yeah. So, let us mark all the points. So, I am going to have 1 2 3 4 5 6 1 2 3 4 5 6. So, let me take these vectors 2 4 is basically okay 1 2 3 4 5 and 6, here again 1 2 3 4 5 6 and that is 0. So, 2 4 is basically a vector in this direction which is here, and 1 2 is this vector, 1 2 is this vector which is also along the same direction, and the resultant, the third vector that we are looking for is basically 3 6, and 3 6 vector is going to be along this direction. Three 6 is along this direction. So, what am I going to have? I am going to have this blue one which is nothing but my first column which is A1, then the purple one is basically my A2, and the green one that I am going to have is basically the B vector. It is along the same direction. I am sorry, it looks a bit out of direction. So, let us just draw that once again. So, 3 6 is basically here. So, let me draw this. 3 6 is also along this direction and that is B. So, what do we see here? We see this, we see that the vector A1, the vector A2 and the vector B are all along the same direction, along the same direction. And if you remember, we had done this vectors which are along the same directions are vectors which are multiples of each other, we call them as linearly dependent vectors. So, in this case we are going to say that the vector 2 4 and the vector 1 2. So, 2 4 can be written as 2 times 1 2 vector. In this case the vector A2 that we had here can be written as 2 times A1 vector, and therefore, we say that A1, the vector A1 and the vector A2 are linearly dependent, vectors. And incidentally, we also see that the vector 3 6 is along the same direction. So, here again we are going to say that okay, we are going to have x1 into 2 4 plus x2 into 1 2 gives me 3 6. We can very clearly see here see the following here. Since we already said that 2 4 is 2 times a1, I can write this as 2x1 into 1 2 plus x2 into 1 2 is equal to 3 6. So we are going to say that 2x1 plus x2 into 1 2 is equal to 3 6. This is what we have, and here we can see very clearly that x1 is equal to 1, x2 is equal to 1, helps gives me 3 6, x1 is equal to 1.5, x2 is equal to 0, again gives me 3 6, x1 is equal to 0, x2 is equal to 3, that also gives me 3 6, and so on. And that is what we have as we call this as infinitely many solutions. Infinitely many solutions. Now suppose we have this case, let us take example 3. This is again the example that we have seen earlier. Example 3, we had 2x1 plus x2 is equal to 3 and 2x1 plus x2 is equal to 4. Now again if we write it in the column format, we are going to get it as x1 into 2 2 plus x2 into 1 1. I want the right hand side to be 3 4. So the question is find scalars such that x1 and x2 such that 3 4 can be written as a linear combination of 2 2 and 1 1. Now here again we see that the two vectors 2 2 and 1 1 are multiples of each other. We see that the vector 2 2 is 2 times 1 1, and we say that the two vectors, therefore the vector a1, I mean by a1 I mean the first column of the matrix. Here of course I have not shown the matrix, I think that is understood. So a1 is equal to 2 2 is basically 2 times a2, which is 2 times 1 1, and therefore we say that a1 and a2 are linearly independent, linearly dependent, sorry, linearly dependent. So essentially what we have x2 x1 plus x2 times 1 1, I must get the value 3 4. Now it is very interesting that whatever that we try to do, the right hand side vector will just be a multiple of this 1 1. There is no way that we will get the right hand side second component to be different from the first component, since on the left hand side we have multiples of vectors whose both the components are the same. The right hand side cannot be a vector where both the components where the components of the two vectors are, of the vectors are different. So this is not possible, and that is exactly where we landed into the idea of where we got into the idea of inconsistency. So this is basically inconsistent system. This corresponds to the inconsistent system. Why is it we said that it is inconsistent system? We cannot find x1 and x2 such that no x1 comma x2, no scalars x1 and x2 exist such that, let us call this as star, that equation is true. So how does this look in the vector way? How does the what would you call, how does the column perspective of this inconsistent system look like, it is very easy to find out. So, we see that let us again draw. So, we have 1 2 3 4 5 1 2 3 4 5 0 1 2 3. So, the first vector that we had was 1 1, then we had the second vector was 2 2. So, this vector is 2 2. So, let me call this 1 1 vector. This was basically my second column of the matrix and this was basically the first column of the matrix. So, I will call this as A1 and A2, and where was B? B was interesting, it was at 3 4, which means it is at this point. So, this is basically my B, that is my B vector. You see that there is no way that I can take combination of A1 and A2 to get to the direction of B, that is not possible at all. So, therefore, this is basically how an inconsistent system looks like. So, this is basically the inconsistent system. Right. So, let us capture all these things in a general form. Suppose I have this, suppose we have, let us say A11 x1 plus A12 x2 is equal to B1 and A21 x1 plus A22 x2 is equal to B2. We are going to write this in the column format as x1 into A11 A21 plus x2 into A12 A22 is equal to B1 B2. Now, so how do our different what we call the different system of equations look like? That means a system with unique solution, infinitely many solutions and no solution look like. So, let us do that. So, system with unique solution. How does that look like? It is basically this. Say I have E2. Say suppose I have my this to be the first column of the matrix, which corresponds to A1, the vector A1, and this corresponds to the vector, let us say A2, the second column of the matrix. Then we have a system with unique solution, because for every B we can write we can find scalars such that B can be written as a linear combination of the two columns of the matrix, namely A1 and A2, right. The reason is like we have already seen that you can complete a parallelogram here, that means it will have a finite area, that means the determinant is not equal to 0. If the determinant is not equal to 0, then we say that for every B on the right hand side you get a unique solution for the system of equation Ax equal to B. So, you can actually complete the parallelogram here. So, you can basically complete the parallelogram, and so you can get for different values. This is a finite area, area is not equal to 0. So, the determinant of A is not equal to 0, where A is this matrix A11 A21 A12 and A22. So, if the determinant is not 0, then we end up getting unique solution. Now, what about a system with infinitely many solutions? Infinitely many solutions. So, how does that look like? So, we have already seen that. We see that a system with infinitely many solution will basically look this way. You have your axis, namely the E1 and E2. So, what I will do is I will draw those. So, suppose this is my A1 vector, that means the first column. The second column of the matrix is a multiple of this A2, I mean A1, and the right hand side B vector that we have is also along the same direction. This is my B vector. If this is the case, then we will have a system which will have infinitely many solutions. The third is where we are going to look at system with no solutions. System with no solutions or no solution. Now, what does this mean? In this case, I can still in the previous case I can still write B is equal to x1 into A1 plus x2 into A2, and I can find infinitely many values for x1 and x2 such that the vector B can be written as a linear combination of these two. So, how does a system with no solution look like? So, that is going to look like this: E1, E2, this is again we are looking at only 2D. So, it is going to look like this. Say I have A1 here and I have this is my A2 vector. However, my B vector is going to be somewhere out there. So, this is my vector B. So, in this case B can never be written as x1 into A1 vector plus x2 into A2 vector. Yeah, this is basically the idea of system with no solutions as far as your 2 dimension is concerned. So, if you want to if there is a system with unique solution, then the 2 columns of this 2 by 2 matrix that we have will actually be, you will be able to form a parallelogram with a finite area, that means non-zero area you will have. That means the determinant of the matrix is not equal to 0, and that means for every B on the right hand side you get a unique solution X for the matrix for the system Ax equal to B. If you look at the system with infinitely many solutions, then you have already seen that this parallelogram that we have here, it has already degenerated to a line. So, which is basically, which means the area is going to be 0. Whether it has infinitely many solutions or no solution, it depends on what is the value of B, the right hand side B vector that we have. If B is also along the same direction as the columns of A1 and the columns of the matrix, then you get infinitely many solution. If B is going to be in a different direction, then you are not going to get any solution at all. One more thing that we looked at when we looked at the system of equation was basically the homogeneous system of equations. Homogeneous system of equations, where we looked at Ax is equal to 0, where this 0 is basically the 0 vector. Suppose I take a 2 by 2 matrix, I am going to look at this as A11, A12, A21, A22 into x1, x2 gives me 0, 0. Now, if we write it in the equation format, it is something interesting turns out. So, we have A11 x1 plus A12 x2 is equal to 0, and A21 x1 plus A22 x2 is equal to 0. If you look at the equation 1 and equation 2 that we have marked here, where you can very clearly see that I can, it is of the form A11 A12 x1 x2 gives me 0. Similarly, I have A21, similarly we have A21 A22 into x1 x2 gives me 0. That means if you look at this this expression that we have here, this corresponds to taking two vectors, the dot product of two vectors, and we say that the dot product of the two vectors is 0. Now what are the two vectors here? The two vectors are basically a11, a12, this is one vector, that is basically the row vector that we have, and the other vector is, let us say, x1, x2. Now what are we looking for? We are looking for that vector such that that vector x, whose components are x1 and x2, such that the dot product of the row vector a11, a12 with x1, x2 is equal to 0. That means we are looking for a vector x which is orthogonal to the vector a11, a12, implies here what we want is they are orthogonal. This is something which we know are orthogonal. Same is the case here. I have this second row vector which I can write it as a21, a22, and the same vector x which is x1, x2. Now they are orthogonal. Now we know that if they are orthogonal, we know that if u and v are orthogonal, two vectors u and v are orthogonal if u dot v is equal to 0, that is u transpose v, or which is same as v transpose u, which is equal to 0, and that is exactly what we see here. So what we want is we want to find out a vector which is orthogonal to both the rows, so both the row vectors. So we want x1, x2, this vector x, such that x dot, let me call that as a let me put this as a r1 is equal to 0 corresponding to the row 1, and x dot a r2, let me put that as 0, that corresponds to the second row. We want to look at this. Now that means we want the same vector x which is going to be orthogonal to both the row vectors r1 and the vector r2. Now one important thing that we know is we already I mean it's pretty easy to figure out that if x were to be the 0 vector, we are going to get x dot ar1 is 0 and x dot ar2 is also 0. That means x is equal to 0 vector. So if x is the 0 vector, then x dot, let me call that as ar1 is equal to 0. Similarly x dot ar2 is equal to 0, that is known. And suppose if x is equal to 0 is the only vector orthogonal, only vector orthogonal to say ar1 and ar2, then we say the homogeneous system of equation, then ax equal to 0 has only trivial solution. Right. Suppose if x is not equal to 0 vector is such that x dot ar1 is equal to 0 and x dot ar2 is equal to 0, then we say ax equal to 0 has a non-trivial solution. So therefore, how does this look like geometrically? We will look at that. So we are going to have this, let me say E1, let me say E2. Suppose I have this vector which is, let us say A1, and let me take this vector which is A2. Now it is interesting to see that these two are basically linearly independent vectors, then the only solution that you will have to the Ax equal to 0 is this guy, and this is basically my x vector. This is only trivial solution case. Ax equal to 0. Suppose if we take this non trivial case, I am going to have A1 here, I am going to have my A2 also along the same direction, A1, A2 also along the same direction. Now, where is my non trivial solution? The non trivial solution will be, it will be orthogonal to this guy. So, this is going to be my x vector, which is going to be orthogonal to both these columns, which will give me that 0 on the right hand side, right. I am going to get the 0 on the right hand side. So, what we essentially have seen in this section is basically how does the system of equations, linear equations in two variables and two equations and two variables look like in the column perspective, and how are we going to say that the system has unique solution, infinitely many solution, or no solution, and how does the homogeneous system of equation look like, and that is what we have seen in this. We are able to very clearly see that if you are able to write the right hand vector as a linear combination of the columns of the matrix A, which is a 2 by 2 matrix, then you say that either it has unique solution or infinitely many solutions. If you cannot write the right hand side vector as a linear combination of the two vectors of the columns of the A 2 by 2 matrix, then we say that the system of equation is inconsistent, it does not have solutions. And we also figured out that if you want to look at Ax equal to 0, the homogeneous system of equations, you basically want a vector which is orthogonal to both the row vectors of a 2 by 2 system, and if the rows are linearly independent, then you see that x is equal to 0 is the only solution, that is the trivial solution, and if the rows are not independent, that means they are linearly dependent, then you are going to have a non-zero vector, a non-trivial solution for Ax equal to 0. So, the other way of looking at all these things is we want to look at Ax equal to 0. So, we want to look at Ax equal to b, again A 2 by 2 system, let us take this A 2 by 2, x 2 by 1 and b 2 by 1. Now, we have seen that in some cases the matrix A is going to transform x vector to the 0 vector, in some cases the matrix A is going to transform x vector to some other b vector, and so on. But what we want is, in the next lecture we will answer this question: can we have vectors u, or let us say vector u such that Au is equal to lambda u. That means the resultant that you get, the resultant vector, or the when the vector u gets transformed by the matrix A, can we get the resultant to be along the same direction as u, but just a scaled version of u, the direction does not change. So, that is where we get into the idea of eigenvalues and eigenvectors, and we will look at that in the next lecture. Thank you.
Can you repeat that last sentence in the next lecture?
Okay. So, in the next lecture we are going to look at I mean this set of constraints where we are going to look at we are answering this question, where in which if you have a transformation A and you have a vector u, is it possible to get the resultant, or can we transform a vector u to a scaled version of the vector u itself? That means Au is equal to lambda u, and that is where we get into the idea of eigenvalues and eigenvectors, and that will be the focus of our next lecture. Thank you.